So what sort of phenomenon has to be happening to cause a standing wave? What is a standing wave in the first place?
Is it kind of like the wave is interacting with itself so the wave won't actually like propagate?
Yeah, you've got a wave, it's interference. You've got a wave interacting with not another wave, but itself, or I guess you might say its own echo. This specifically takes place in confined regions. Like let's say you've got a room that's enclosed. So you've got a wall, you make a sound, the sound goes towards the wall and echoes. And so you've got sound going one way and its own echo traveling the other direction. So it's interfering with itself, or rather interfering with its own echo. So this tends to happen with sound, it's like sound in air in an enclosed room. Or if you have waves traveling on a string, but let's say the string is fixed on both ends. If you've got a string that's tied in place on both ends, like if you just got like a nail and a nail in the wall and you stretch out some string between them and stretch it tight and tie it off, you can create a standing wave just by plucking the string. What you do when you pluck the string is you create vibrations in the string. And let's say you've got vibrations as a wave traveling one way and the echo of those vibrations bouncing off of the peg or nail or whatever it is. And they keep bouncing back and forth. But you've always got waves traveling in both directions interfering with each other. And if you set it up right, the interference ends up following a very specific pattern. If you've got like a crest traveling one way and a trough traveling the other way, what's going to happen when they intersect? What kind of interference would that be when they actually meet?
Constructive?
Yeah, when they meet, crest and trough, you're going to get destructive interference. They'll cancel out, so you'll get a flat dead zone. Or if you've got a crest traveling one way and another crest traveling the other way, when those meet, what's going to happen?
Constructive.
Yeah, you get constructive interference. They add together to get a very large crest. Or alternatively, trough and trough. Those are going to meet to get a very large trough. So that would also be constructive interference. So these might end up just being a sort of random looking jumble of constructive and destructive interference. But if you set it up exactly right, then there are certain locations that are always going to be constructive interference and other locations that will always be destructive interference. And one of the requirements here, since this end of the string is nailed in place, this end cannot vibrate. So what type of interference has to be happening at that endpoint?
Destructive.
Yeah, if the endpoint is nailed in place and cannot move, that's always going to be destructive interference. Same thing with this other endpoint. On the other hand, if the end were free to move around, then that endpoint would always be constructive interference. In this case, it's not free to move, so we call that a node. A location where it's always destructive is called a node. And then a location where it's always constructive as time passes is called an antinode. And the simplest way to have a standing wave, like in a situation like this, where it's fixed in place on both ends, is to have a node on one end, a node on the other end, and an antinode in the center. So let's assume that the exact center is an antinode. They've got to be evenly spaced. Node, antinode, alternating. So let's say we've got nodes on the ends and an antinode exactly in the center. Antinode means this piece of string is oscillating wildly up and down, whereas the endpoints are staying in place. And ultimately, the reason why this is called a standing wave as opposed to a traveling wave is that as the wave and its echo travel past each other, any single point is either going to be staying still or oscillating wildly all the time. So it looks like just oscillating in place. It doesn't look like the wave is traveling. So we call this a standing wave in the sense that it's vibrating, but the wave does not appear to be moving forward at all. So what this is going to look like, you're going to get one location in the center that's wildly oscillating, an antinode, points on the ends that are staying still, nodes, and then in between you get partial interference. So maybe a little bit of vibration, more vibration, And this is going to end up shaped kind of like a sine or partial sine wave of its own. So this is the sort of diagram we usually use for drawing a standing wave. And this represents essentially the borders of how far the string can travel. This part of the string can travel as high as here and as low as here. This piece of string can travel up to this high and down to this low. This point can't travel up and down at all. So what's really happening, and you can't really see this with the naked eye with like a guitar string because it's vibrating so fast it just looks like a blur. But if you slow that down, you can actually see the string pulsing up and down like this. And so these curves basically represent the limits of how high it goes and how low it goes. And we sometimes draw one of those curves as a dotted line to distinguish between them. Any questions on the diagram so far? And we usually call this the n=1 state, or sometimes the fundamental mode, or fundamental vibration. This is basically the simplest type of standing wave we can have on this string. And then if we want to look at the next more complicated case, let's say we have another copy of the exact same string. We still have to have nodes on the ends. But to make this one step more complicated, let's assume we have one more node, which would be in the exact center because they've got to be evenly spaced. So one more node, and then exactly halfway between nodes, we should expect another antinode, another constructive interference spot. And likewise, halfway between those. So this is going to look something like this. And again, these curves basically represent the borders, the highest and lowest the string can go as it vibrates. So instead of vibrating like this, like in the fundamental, it's going to be vibrating like this, if that makes sense. You got one point in the middle that's not moving up and down at all, 2 points here that are moving up and down very quickly, but opposite in phase to each other. And then the endpoints are also destructive, not moving at all. And then this would be called the n=2 case, the second harmonic. Or sometimes called the first overtone, in the sense that it's the first one over the fundamental harmonic. So fundamental mode is also called the first harmonic. And then the next case, the next more complicated standing wave would be the second harmonic, sometimes called the first overtone, but I find that kind of confusing because it is the n=2 case. Any questions on those so far? And then we could go to the next level if we add in a little bit more complication. If we still have nodes on the ends, of course, but instead of having just one node in between, let's say we put in 2 nodes instead of just 1. Equally spaced, of course. And halfway between adjacent nodes, we're going to have antinodes. So that's going to look something like this. So now we've got these three locations that are wildly oscillating up and down. And then points in between that are not oscillating at all. This would predictably be called the n=3 or third harmonic. Or somewhat confusingly, perhaps the second overtone. And we could keep this going. We could have fourth harmonic, in which instead of just having 2 nodes in between, we have 3 nodes in between, all evenly spaced, and antinodes between those. So that represents a progressively more and more complicated sort of vibration. Same overall pattern, we're just adding in more pieces. And so you could do this for as many n values as you want. N equals 5, n equals 6, n equals 7, 8th harmonic, 9th harmonic, 10th harmonic. And what's happening to the wavelength as we progress towards higher and higher harmonics?
They get shorter.
Yeah, the wavelength is getting shorter and shorter and shorter. In fact, if we actually draw out the wavelength here, the wavelength is mathematically very predictable. If we have, like for instance, one wavelength here would be this far. One wavelength here would be this far. One wavelength here would be the whole string. And one wavelength here would actually be the whole string and then some. Because one whole wavelength would have to go through a full cycle of equilibrium to crest to equilibrium to trough to equilibrium. So for n equals 1, the wavelength is actually longer than the string itself. One full wavelength that doesn't even fit on the string. But then if we go further and further into the harmonics, the one wavelength becomes a smaller and smaller and smaller fraction of the complete string. Any questions on that so far? So to predict how long the wavelength is going to be, it's very useful to look at this not in terms of whole wavelengths, because notice that like here, we don't even fit a whole wavelength. Here we've got a full wavelength and then less than another wavelength. For these standing waves where you're starting and ending at a node, I find it more useful to look at it in terms of half wavelengths. Like for instance, for n equals 3, we've got a half wavelength, we've got another half wavelength, we've got another half wavelength. So that's 3 copies of a half wavelength. 3 times a half wavelength equals the length of the string. And let's call that L. L in this case is, let's say, the length of the string. And then for the n equals 4 case, we've got 1, 2, 3, 4 half wavelengths. 4 times a half wavelength equals the length of the string. For n equals 2, 1, 2 half wavelengths. So 2 times a half wavelength equals length of the string. And then for n equals 1, this whole thing is just one single half wavelength. 1 half wavelength equals the length of the string. So this is a very convenient and consistent way we can write out the wavelength in terms of the length of the string. We've got the whole string is 1 half wavelength, or the whole string is 2 half wavelengths, or the whole string is 3 half wavelengths, and so on. In fact, what if we were looking at like the 7th harmonic? What would the equation look like for that one? If we're looking at n equals 7.
7 times half wavelength equals L.
7 times half wavelength equals length of the string. And in general, just the number we're putting in here is the harmonic number. In fact, for waves like this, if it's fixed on both ends, if both ends are tied in place and have to be nodes, which isn't the only form of standing wave, but it's the one we want to take a look at right now. For that type of wave, standing wave, the n value can be interpreted as the number of half wavelengths, the number of half cycles there. So in general, we usually call these fixed standing waves. Fixed in the sense that it's fixed in place on both ends. Both end points are unable to move. N times the half wavelength is going to equal length of the string, where n can be any whole number, any positive whole number, and corresponds to the harmonic number, the label we're assigning to it. If you then solve that for wavelength, what do you get? How would you isolate L or lambda there?
2L over n.
Yeah, multiplied by 2, divided by n. So the wavelengths form this nice neat pattern. Wavelength could be 2L over 1, 2L over 2, 2L over 3, 2L over 4. So we have a general formula for the wavelength of any standing wave on this string. And we usually call that lambda sub n to emphasize that it depends on the value of n. So for instance, we'd say lambda 1 equals 2L over 1. That's just 2L. Lambda 2 would be 2L over 2, so that's just L. Lambda 3, 2L over 3, so that's 2/3 L. Lambda 4, we plug in 4, 2 over 4 reduces to 1/2. So we get half a wavelength, or half the length of the string. And that corresponds to these single wavelengths we drew in. This full wavelength is 2/3 of the length of the string. This one, this wavelength, is half the length of the string. This wavelength is the length of the string. So the wavelength is very predictable in cases like this. There are only certain specific values it can be. The in-between values don't work because they don't form standing waves. For instance, between L and 2/3 L, you might have, let's say, 3/4 L. But 3/4 L does not work as a wavelength here because it doesn't fit into this pattern. This is a discrete situation rather than continuous. Discrete in the sense of you can have these values, but only these values. The in-between values do not work because they're not the right wavelengths to form standing waves on this string. Any questions on that so far?
I have a quick question. So since the wavelengths are fixed because it's a fixed length for the string, so does that also mean that the frequency is fixed as well?
Yes, the frequency is this only allows certain frequencies too. And frequency is often going to be more useful to look at here. Because if we're talking about like using a stringed instrument to create a sound, you don't listen to the stringed instrument by like putting your ear on the string. The wave travels from the string through what other medium to get to your ear?
Through the air particles?
Right, it becomes a sound wave traveling through air. So we've got multiple media here. We've got the wave is created in the stretched out string vibrating. The vibrations of the string cause the air molecules nearby to vibrate, and that disturbance causes a traveling wave. So the standing wave in the string creates a traveling wave in the air around it. That traveling wave reaches your ear and transitions from traveling wave in the outside air to a traveling wave inside your ear, which then turns into vibrations in your eardrum, which turns into nerve signals, which allow you to interpret that sound in your brain. So this information, this pattern is traveling through several different mediums. And as you transition from medium to medium, the wavelength can change, but the frequency doesn't. So even though wavelength is what we can calculate directly from the length of the string, frequency is what we actually want to find, because that's what you're going to hear. That's what doesn't change as the wave transitions from medium to medium. So how do we convert wavelength to frequency?
Can we use the formula that V equals wavelength times frequency?
Yeah, that should work great. Speed equals wavelength times frequency. We have the wavelength, so we can plug that in. And then how would we isolate frequency there?
You would have V times N divided by 2L?
Yeah. So this would be the frequency of the nth harmonic, where V is the speed of the wave, specifically the speed of the wave in the string, because that's where it's being created. On the other hand, if you're talking about a wind instrument, you'd be using speed of sound in the air inside the flute or penny whistle or whatever, because that's where the sound is being created. But generally, this V is speed of the wave in the medium where the standing wave is being created, in this case, the string itself, times N, which can be any positive whole number, divided by 2L, where L is the length of the string. And so frequency is also discrete, or sometimes we say quantized. Quantized meaning only specific values work and the in-between values do not work. So frequency is quantized, only certain specific values work for frequency, other values do not form standing waves, so they're not going to happen. Any questions on that so far?
Casey, so we know that velocity, like in the equation Fn equals V times N over 2L. Mm-hmm. we know that velocity is changing, right? Because it's changing mediums?
Well, not in this equation. The v in this
not.
equation specifically refers to the speed of the wave in the medium in which it is created.
Okay.
As it transitions, the wave is going to change velocity as it goes from string to air outside to air inside your ear to your eardrum. The speed is going to change, but the frequency, once it is, like this is the frequency that is established by the string. Once the wave leaves the string, it continues to have that same frequency, even though other variables can change.
Okay, so it could be like when you talked earlier today, it was like F1 equals F2, like different, the same frequencies, but different mediums, kind of, right? Like,
oh yeah, that was when we're talking about the transitioning from string to air.
Yeah.
It has to stay the same, because as the string vibrates at a certain frequency, it causes the air molecules around it to vibrate at the same frequency. Yeah, the string vibrating at a certain frequency causes the air nearby to vibrate at the same frequency.
Okay.
And so the traveling sound wave that's created in air is going to have the same frequency as the standing wave that exists in the string. That frequency does not change as the wave moves.
Okay. Thank you.
So that's really what this formula is talking about. This formula is describing how the properties of the string itself create a certain frequency that will work, or a certain collection of frequencies that will work. As those frequencies are created, they travel out as sound that you can hear, but the properties of the string determine what notes you actually hear. In fact, let's try actually using that formula on these examples, on these specific strings, now that we have a formula for it. We know that the frequency of the nth harmonic is speed over 2L times n. And I find it very convenient to write it in this format, to split the n out of the fraction, because v over 2L is going to be a constant for that string. So we just have whole number multipliers times that constant. So frequency 1, the frequency of the harmonic, often called the fundamental frequency, is going to be v over 2L times 1. We would just plug in 1 for n. And what this provides, this tells you what the lowest note that this string can produce is. Because all of the other ones are going to be v over 2L times something larger than 1. So they'll all be higher frequencies. This is the smallest possible frequency corresponding to the longest possible wavelength. And that means the lowest possible note you can hear from this string. Plug in 2, we get v over 2L times 2. In other words, F1 times 2. Plug in 3, we get v over 2L times 3, which is the same as the original fundamental frequency times 3. And then v over 2L times 4, which is just the original fundamental frequency times 4. So when you pluck a string on a stringed instrument, you're actually producing all of these frequencies. In fact, you're producing more. When you just pluck a string on a stringed instrument, you're not really choosing a frequency. You're just causing a chaotic jumble of the string. You're creating many frequencies at once, but only these frequencies actually propagate. All the other frequencies that don't fit this equation die off quickly because they don't form standing waves. But these frequencies, and then F5, F6, and so on, create standing waves that last for a long time. Let me demonstrate. I've got a mandolin here. So this string has a certain speed of the wave in that string. It has a certain length. If I pluck it, it creates a sound, not just one sound though. The richness of that tone is coming from the fact that it's actually creating many frequencies at once. Mostly when I pluck the string, you hear the lowest frequency, the fundamental frequency. But you also hear a sort of a resonance of other frequencies pitching in a little bit as well. And the reason why these frequencies sound good together, if you compare these, what's the transition from the fundamental frequency to the second harmonic. What's the multiplier there? Like to get from F1 to F2, what are you multiplying by?
2.
Yeah, that's a ×2 multiplier. And a ×2 multiplier, if we're increasing the frequency, generally what do you hear differently if you increase the frequency? Increasing the frequency means you're going to hear...
Like a higher pitch?
Yeah, a higher pitch. This is going to be a higher pitched note. And specifically, if it's ×2, a consistent multiplier leads to a consistent increase in pitch. And specifically, ×2 represents an octave. So an octave is going to sound like... yeah. It's a little bit out of tune. So an octave is 2 notes, essentially the same note in 2 different, like a G and then the next G up. So if you exactly double the frequency, you go up by exactly 1 octave. So any single string is going to produce this note, but also exactly 1 octave up. And then if we look at the next transition, if we go from F2 to F3, what multiplier will change 2 to 3?
The 3 halves.
Yeah, 3 halves, or 1.5. And since that's another nice, neat, tidy fraction of small whole numbers, this is also going to be a pleasant sound together. These 2 notes sound good together because it's essentially the same note 1 octave apart. These 2 notes are going to sound good together because it's another simple ratio, to the ratio of 2 to 3. That's specifically, if I remember correctly, I think that's a major 5th. So it's notes that sound good together because they form these nice, neat whole number ratios. And then if we go from 3 to 4, what's the multiplier there?
.75 maybe?
Or the other way around, because if we do
4/3.
Is it 4/3?
1 1/3, 4/3, or 1 1/3, that's another nice, neat multiplier, or a nice, neat ratio of simple, small whole numbers. So this is going to be another pair of notes that sound good together. I think that's a major 4th, if I remember correctly. But also, more to the point, if you go from F2 directly to F4, what's the multiplier there?
2.
Another ×2, which means that's another octave. So that means when you pluck this string, you get not only this note, but also 1 octave up, and the same note another octave up, and this pleasant major 5th in between. And then more nice, neat whole number ratios or beyond that as well. So since the string is producing these multiple notes, but only these nice, neat, simple ratios of each other, we end up with this note that has other notes that sound good with it. And this is the foundation of how chords work. This is the foundation of music theory. This is why certain notes seem to sound good together. And if you want to adjust those, like let's say this is out of tune. If I'm playing some note, that doesn't sound quite as nice as it should. It doesn't sound like quite the right note. So what could I do to adjust the frequency? If we go back to this equation, what could I change about the string's properties to change the frequency that it produces?
Would it be adjusting the length of the string?
Yeah, one way is to adjust the length. And this is actually how you get different notes on most stringed instruments. If you pluck a string, it creates the fundamental vibration, fundamental harmonic. But you can shorten the string by fretting it. So if you just pinch the string here, you're making the effective length of the string shorter. If I pinch it here, I don't have the whole string vibrating, I just have this much of it vibrating. So you can adjust what note you're producing by changing the length of the string while you're playing it. But in order to tune it, like if the bass note itself without any frets is not quite right, I can't really change the length. I'm not like adjusting how large the instrument is, but I can adjust the speed. What properties of the string do you think determine the speed of the sound in the string? Like if I can modify, how do you tune a stringed instrument like this? What do you adjust on it to change the pitch slightly?
How tight the strings are?
Yeah, how tightly stretched they are. That's what these tuning pegs up here are for. Let me make sure I got the right one. If you tighten or loosen the string, listen closely as I turn this. You can make subtle changes to the pitch before you play. You don't want to try doing this while you're playing it, but you can tune it by tightening or loosening the string, because the tension of the string influences the speed of the wave, and the speed combined with the length influences what frequencies you get. So this is how you change the pitch of the string. If you just want to make small changes before you start playing to make sure it's in tune, you adjust the speed by changing the tension. And then while you're playing, you adjust the note by putting a finger on a string to pinch it off, making only this much of it vibrate. So you're changing the effective length. And then by pitching certain strings in the right direction, you can get chords. And that's, again, just certain notes, deliberately putting together certain notes that sound good together because they fit nice, neat whole number multiples of each other patterns like these. So the whole entirety of music theory is based on the physics of standing waves. We didn't really learn that until centuries after we started playing music in the first place, but this is ultimately why it all works. Any questions on that? All right, so that's the basics of standing waves. We can look into more examples next time. Feel free to email me if you have any other questions, and I will see you next time.
Thank you.
You're welcome.